Hello. This is Project 9, Compactness in Application. It's a project done by Paola Segovia and me, Ismael Arroyo. I hope you all like it. Okay, so this is the table of contents. We're going to try to cover one, the definitions, theorems, and the importance of this project, the application in economics, the application in physics, the application in astronomy, little homeworks that we're going to try to cover, and our references. Let's start with the definitions. These are the definitions that we're going to be covering, which are open cover, compact set, closed set, bounded set. Here are the definitions. All right, let's go ahead and go with the theorems. We're going to be covering the Heimburg theorem and the extreme value theorem. The Heimburg theorem is the bridge between extra compactness and practical optimization, which we need, which um, links with the extreme value theorem, which in which we get the maximum and the minimum in a continuous function, right? So the motive and the importance, right? So imagine you become an astronaut, right? Um, or you're the scientist sending astronauts to space, right? And your job is to see how much fuel you're gonna use to send them up in space, right? Or they're gonna use to drive the spacecraft, right? Because they want to either visit one of the spacecrafts or satellites that are in the space, or they want to reach the moon, right? Take pictures, stuff. You want to be able to maximize um, the amount of fuel you're gonna buy, right? So that you can be able to send them there, but minimize the usage of it, right? So let's say you're like, okay, how much fuel can I buy with the money I'm given, or with 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 the budget that we have, right? Um, and how much fuel do I actually need, right, to be able to reach where I'm going, right? Or wherever I'm sending these people, right? And one of the reasons is because there's laws against using uh, burning fuel, right? Because it damages the ecosystem, right? And two, maybe the budget in this project is minimal, so you want to use as little as possible so that you can use the extra money that you have in another part of the project that might need uh, uh, a little extension in the budget, right? So uh, you can have a company, you can be an entrepreneur, and you have your product, right, and you have your materials, right? So you want to maximize these profits that you have, right? Because you have a revenue, which is when you sell your your product, right? And you have your costs, right, which is the materials, right? So whenever you sell these products, um, and you subtract the costs, that's when you have your profit. And now you want to grow as a company because, I mean, you always want to grow as a company because that profits you, right? Um, or let's say you don't even have to be a physicist. You can just be somebody that's trying to maybe uh, find an equilibrium in a system. For example, somebody that works with computers would find an equilibrium um, in the thermodynamics that happen in cooling down a processor, for example, because there's a limit to the amount of cooling that you can give a processor before it freezes, and there's a limit that you can have a processor heat up to, right? So you want to find that equilibrium in which the processor works at its best, right? Not cool enough so that it can freeze and glitch, or not hot enough so that it can burn up, right? So we have a maximum and a minimum in the temperature that you can get this processor to, but you want to find the equilibrium in which this processor works best. So comparing compactness will guarantee the existence of these optimal solutions in which um, either the processor or the fuel or the cells that you have um, are at its best and give you the best solution. Um, it gives you a stability for these models, right? And it gives you reliability, that sense of confidence that you're gonna have the best results, right? Um, and that it's doable, right? In the real world, and when you have to make decisions that cost money, right? It's when you have the most pressure. So it gives you the confidence to do it, to say, oh, it's doable, right? So let's say you have a company that produces two products, right? Um, and you have a um, the company itself reduces or limits the production to x plus y equals less than or equal to 100, x and y being the two products, right? X being one and y being the other, with x being greater than or equal to zero in the amount of products that they make, and y being greater than or equal to zero with the amount of products that they make. Now imagine that the production function is this: the production of x and y will equal to 50x plus 40y minus 0.2x squared minus 0.1 y squared. Like, now, what would be the optimal solution, right, for this, for these two products to work, right? Um, and why does compactness appear here, right? The feasible region will be where x and y, right, are greater than or equal to zero, and them together are less than or equal to 100, which is closed and bounded, right? Therefore, right, therefore they're compact by the Hain-Borel theorem, right? Which the definition is up there in the previous. It's in the previous uh, slide. Now, since P is continuous, the extreme value theorem guarantees you a maximum profit exists, right? Or maximum production actually exists. So something to talk about is what would happen without compactness, right? What do you think? Well, um, let's say in a company, right, that makes and sells product, right, you have unlimited production, right? Let's say, would that be correct, right? No, because you keep on making this product, right? And what if it doesn't sell, right? What if, uh, what if everybody buys that product and everybody has it, right? And you keep on producing. Who are you gonna sell it to? Everybody has it, right? And if it doesn't break, it has durability. What if it never breaks, right? And nobody ever needs one anymore, right? So unlimited production would be something to think about, right? Like, okay, how many am I gonna make per day, right? So that there's what's it called, there's a need for it, right? Uh, and I can probably sell them at a higher price, right? Um, well, now, if there's unlimited production, right, you can't really say, oh, I can guarantee you're gonna reach a maximum profit, right, per year, right? You're gonna say, okay, if I have an unlimited amount of production, okay, this year I'm gonna make this much, right? No, you can't say that because you can keep on producing, and maybe there's people that will keep on buying or will not buy at all, right? And will you have a profit or a maximum profit when nobody's buying and you're just having costs? Maybe not. If people keep on buying and buying and buying and buying, will I be able to reach a maximum profit? Probably not, because you can't predict, right? So let's say you're a starting company, right? And you want to have people invest in your company, but you can't give them a maximum profit within a year. well, nobody's gonna want to invest, right? Because it's gonna be a dangerous let's say investment, right? um, and what can happen, optimization software may fail, right? In such cases, right, optimization, let's say you're gonna try to predict, right, uh, how much profit you're gonna make within a month, maybe within 2 months, maybe a year, right? And let's say you have a limited amount of production, right? You can't say, okay, i'm gonna make this much product, right, and I'm gonna have this much profit, because you're gonna keep on making more and more and more and more and more and more and more, and you don't know if all that product will sell, right? So for the optimization software, the software is gonna be like, okay, you're just gonna have cost, because you're still producing and you're still producing, and you're just gonna keep on recurring costs, right? So it's gonna fail. It's gonna tell you that you're gonna have a zero profit, right, in its view, like for the next month, for the next 2 months, for the next year, right? It's gonna tell you you're gonna have zero profit or maybe negative profit, and it's gonna be like, what? Probably millions of negative profit if it's within a year. And well, it failed. It's not a realistic what's it called, um, hmm, uh, prediction for your actual profits or your actual costs, right? Now, this is why businesses impose realistic constraints. Let's say I'm just gonna produce this much of my what's it called, of my product, right, within this year, and that's all I'm gonna sell, right? Now, if I sold this much within this year, next year I'm gonna sell more and see if everything sells. If I reach a year in which I sell less than what I added to the amount I'm gonna sell, then that's my maximum sales, right? And with my maximum sales, I'm gonna say, okay, I'm gonna reduce the amount of sales I'm gonna have and higher the prices. That way, I reach an equilibrium in which I don't have to produce that many, right? And I'm still getting the same amount of money, and the same profits, right? And that will reduce my costs, but it will higher my profits because of the revenue, right? So that's where uh, businesses make those realistic constraints, because they want to make money, make make less of the product, sell at a higher price, and that's where they make money, right? So here's a practice problem. The importance of compactness is important in business because companies make decisions under real limits, such as product capacity, labor, materials, storage, and demand. These limits create a feasible set of possible choices. When the feasible set is closed and bounded, such as an interval from 0 to 1,000, it is compact. Um, this matters because if a profit function is continuous on a compact interval, then a maximum profit is guaranteed to exist. In business terms, right, compactness helps guarantee that there is a best feasible decision. So, like applying it again to real world application, um, a wireless charger manufacturer wants to decide how many chargers to produce and sell each week to maximize profit. Because of factory capacity and material limits, the company can produce between 0 and 1,000 chargers per week. So let's have Q represent the number of chargers produced and sold per week. Our constraint would be that the amount of chargers Q, right, will be between 0 and 1,000. So it could be greater than or equal to 0 or less than or equal to 1,000. This interval is compact because it is closed and bounded, right? So that's how we would apply it in real life. Now, continuing the problem, right? Um, we're going to have a price demand function, the cost function, the revenue function, and the profit, um, which is the revenue minus cost. That's another function. And now to maximize our profit function on the compact interval from 0 to 1,000, we're going to have to use the or take the derivative of our profit function, right? Set the derivative equal to 0 and compare the critical point and endpoints of this function, right? Usually it's best done using uh, a graphing calculator like Desmos, where you can see, right? And uh, we end up with the largest value, right? Would be 27,500. So the maximum profit occurs when the company produces and sells 750 chargers per week, right? So here's a visual representation of the weekly output for the wireless chargers, right? And we can say that it's between 0 and 1,000, right? And we can see that it reaches a maximum output between 0 and 1,000. Not in either of the endpoints, right? But at actually 750, and it gives you a $27,500 profit, right? And that's where you want to stay. You don't want to stay at 1,000, making 1,000 chargers, and it gives you a profit of 20,000. So with making less, which is 750, you actually make more money, right? The profit will be 7,500. And if you actually make zero chargers, you end up with a loss, right? At negative 4,000, negative 40,000, right? So you wanna actually make as much as possible. So we have applications in physics like potential energy and equilibriums, right? Um, where you can have a particle that moves in a potential field, right? And physicists will seek the minimum, right? So that they can find stability, right? Because systems naturally move towards a minimum energy. Suppose a particle is confined to um, the set of numbers from -3 to 3, right? Uh, Saying that there's actually no energy or less than no energy. They're putting energy by itself, right? If it's negative, the particle is moving itself, and if it's positive, right, you're actually inputting energy yourself, right? Um, what does this tell us, right? Let's think fast. What are some systems, structured games, designs, think everything, right, or overall, that also move towards minimum energy? Pause or yeah, pause the video. Now, bridges do not vibrate forever, right? That's an example. Pendulums settle. Molecules seek stable configurations. These are examples where um, you want to have uh, you want to seek the minimum of potential energy, right? To find that equilibrium, right? You don't want a bridge to vibrate forever, right? Because it can break down, right? You want a pendulum to settle because you don't want the pendulum to keep on going click 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 click. No, there's what's um, there's a physics called friction, right? That makes this pendulum settle, right? Um, um, you have molecules seeking stable configurations, right? Because if not, um, you're gonna have unstable configurations which can cause explosions, right? That's when you have um, oxygen and other um, chemicals or other um, yeah, other chemicals in the chart bond and create explosions. You have an unstable um, configuration right there. So let's have a practice problem, right? The importance compactness is important in physics because physical systems often have natural limits. For example, an angle, speed, distance, or time period may be restricted if the function describing the system is continuous on a closed interval, then a maximum or minimum value exists. In the real world application, a physics student wants to launch a ball so that it travels the greatest horizontal distance. Assume ideal projection motion, no resistance, same launch and landing height. The projectile range depends on the launch angle, and under these ideal conditions, the range is maximized at 45 degrees, right? So let's think about that, right? Um, so you're gonna have a launch angle for the ball, right, or the object, and you can shoot it horizontally, you can shoot it upwards, right? And let's have the the speed be 20 meters per second, the force of gravity being involved, which is 9.8 meters per second squared, and we're gonna have our range function be 20 meters per second squared divided by 9.8 meters per second squared times sine of the theta, and theta being between 0 and 2 pi. Um, Now let's maximize it, and we're gonna use a derivative for that. We're gonna derive that r of theta, right? And we're gonna have r prime of theta be equal to 400 over 9.8 times 2 cosine of 2 theta, right? So we can set it equal to theta be equal to 0. We can have it set it up um, theta being equal to pi over 2, pi over 4, or the endpoints, which are 0 and pi over 2, right? Um, and check where our data leads us, right, to. Um, so 45 degrees, and at, uh, at 45 degrees it gives us 40.82 meters. At 0 degrees it gives us 0, and at pi over 2 it gives us 0 as well. So let's continue. This would be a visual representation of the physics application of maximizing the projectile range, right? You have your constraints, you have your range, your conclusion, right? Um, given uh, you're given initial speed and gravity, right? Um, and for a projectile launch and landing at the same height with fixed speed, the range is maximized at 45 degrees. That's that's the key insight, right, for all projectors, right? And that's what we learn from here. So in astronomy, let's talk about satellites. Um, the James Webb Space Telescope and the Lagrange points. The Lagrange is talking about the satellite, right? NASA positioned the telescope near the L2 Lagrange point, right? You can see the satellite there and the picture. And at these locations, the gravitational force is balanced, the fuel consumption is minimized, and observations are optimized for the satellite. Right? Engineers consider a constrained region for of space, right? And the cost function may involve um, x, y, and z, right? So that's why you have X could be fuel, Y could be the radiation exposure, and Z the communication delay, right? Because you still have to talk to the engineers and well, basically astronauts that are in the Lagrange satellite. The space region is bounded, right, and closed. Those the compactness, right, because the search region is bounded and closed. Right? So you have compactness there. Since the cost function is continuous, compactness guarantees the existence of the optimal location. Why is this interesting? The reason engineers know that, or engineers know that the optimal location is exists is essentially the same theorem from real analysis. Right? So that's why this is interesting because we covered it at the beginning, right? The theorems. So, all right. So, compactness is important in astronomy because astronomers often work with bounded observation windows, distance ranges, or safe orbital regions. For example, a telescope may observe an object only during a certain time, or a spacecraft may operate only within the safe distance range from the sun. NASA explains that light intensity follows an inverse square relationship with distance, meaning brightness decreases as distance increases, right? And um, basically, the radiation also from the sun can also um, like for example in the telescope that we talked about right now, it can burn the chips inside the telescope. So it works for NASA to have a safe distance from the sun. um, Now, in a real world application, a telescope or spacecraft wants to receive as much light as possible from the sun or another light source. Suppose the safe distance range is from zero point 0.8 um, AU to 2.2 AU, um, which are astronomical units. Yeah, okay, where AU means astronomical units, right? Um, so let's suppose that. Right? Now let's work out this problem with a solution where let's have the distance or in astronomical units um, r, right? The constraint will be between zero point 0.8 and 2.0 for r, and suppose that the relative brightness is modeled by um, b of r, right? Now let's maximize it. Take the derivative and check the endpoints, right? Zero point 0.8, 2.0, and um, it just so happens that the maximum brightness occurs at zero point 0.8 astronomical units. And compactness matters because the closed interval between 2.8 and 2.0 guarantees that the maximum brightness occurs at an actual allowed distance, not outside the safe range. So here we have a visual representation of our problem, maximizing the received light for our satellite, which is well, not just a satellite, it's just um, a telescope, right? We have our constraints, the brightness function, and our conclusion, right? Um, the brightness at different distances are shown, right, within the constraints, and we can say that to maximize the received light within the safe interval, to operate at the nearest allowed distance will be at zero point 0.8 astronomical units. So let's have a homework set maximizing the range of a soccer pass, right? Here's the problem, right? And uh, you can work on it and composite. Now, the reflection questions will be that why is the interval compact? Why does the compactness matter when trying to maximize the range? Um, what do the endpoints um, uh, of 0 over theta um, or theta equaling 0, theta equaling um, pi over 2 represent um, physically? And why might the best angle in real life be different from a mathematical answer? Um, Here are references. We use NASA, OpenStax, and Rudin for our problems and examples. thank you. Do you have any questions?